Welcome to The Explainer. Today, we're diving into a really cool research paper that's all about changing how computers solve problems. We're moving away from finding just one best answer to discovering an entire universe of great ones.
Okay, so let's just jump right in. We usually think about optimization as this big hunt for a single peak, right? The one perfect solution. But what if that's not actually what we need?
You know, in so many real-world situations, having a whole collection of different high-performing options is way more useful than just having one. And that's the exact problem that this new family of algorithms is built to solve. This whole approach is called quality diversity, or QD. So instead of just trying to climb the single highest mountain, QD algorithms are all about mapping the entire mountain range, finding the highest point on every single peak, in every valley, and on every ridge.
So here's our game plan for this explainer. We're going to start with the core idea, then see how a simple QD algorithm works, we'll put it to the test, and finally, we'll uncover its surprisingly powerful nature.
So how do you actually go about collecting this big, diverse set of solutions? Well, the paper we're looking at focuses on this beautifully simple approach called map elites.
Let's try an analogy here. Imagine you have a giant shelving unit with thousands and thousands of little bins. Each bin is specifically for one type of solution. So, for example, you might have one bin for solutions that are really fast, and another one for solutions that are super energy efficient, and so on. The algorithm itself is actually incredibly intuitive. It basically just keeps creating new solutions and figuring out which bin they belong to. And this process perfectly illustrates the two main goals, quality and diversity. See, if a bin is empty, boom, the new solution goes right in. That's a new type of solution we've never seen before. But if the bin is already full, we only keep the new one if it's better than what's already in there. So over time, our collection gets both more diverse and higher in quality. It's really elegant. Now, an algorithm that's simple and intuitive is great and all, but does it work? And maybe more importantly, how fast is it? That's exactly what the runtime analysis in this paper sets out to prove. To analyze it, the researchers used a classic test environment where solutions are just simple strings of bits, zeros and ones. The bins are defined by a really simple feature, just the number of ones in the string. So you end up with a bin for solutions with 0 ones, a bin for 1 1, 2 ones, and so on. And here's where it gets really interesting. It's about how we measure success. The researchers looked at two key metrics. First, cover time, which is just how long it takes to get something in every bin. But then there's the much harder goal, optimal cover time, which is finding the absolute best possible solution for every single bin. So, the bottom line is, for a standard problem called OneMax, the analysis showed that the algorithm's performance isn't just good, it's predictable. We now have a mathematical proof for just how efficiently it can fill up that entire map with optimal solutions. Okay, so it works on a simple test case. Fair enough. But what about the kind of complex, messy problems that we actually see in the real world? Let's crank up the difficulty and see what happens. First, they tested it on something called sub-modular functions. Now, these are a class of notoriously hard problems. And the result? This simple QD algorithm efficiently finds a solution that is guaranteed to be within a certain percentage of the perfect answer. That's a huge deal for problems this tough. Next up is the minimum spanning tree problem. The easiest way to think about this is finding the cheapest way to build roads to connect a whole bunch of cities. The goal is to connect everybody with the absolute minimum amount of road. And here, the feature they used for the bins was really clever. It was the number of separate islands, or what we call connected components, in the graph. This setup basically guides the algorithm to gradually connect everything together. So at the very beginning, the algorithm is exploring solutions that have lots of separate components. You can think of this as the every city is its own island stage. Then, it starts finding better and better solutions that reduce the number of components. It's effectively building bridges between all those islands. And finally, it zeroes in on the bin for one component, which is where it finds the minimum cost spanning tree that connects all the nodes into one happy network. This all brings us to what I think is the most powerful insight of the entire paper. This simple collection of bins algorithm was put head-to-head with some much more complex, established methods. So on the left, you've got our simple QD algorithm. And on the right, you have a powerful but way more complicated optimizer called GSEMO. The shocking result? For these really hard problems, the simple QD algorithm performed just as well.
I mean, the authors themselves really highlight this. They found that their much simpler approach gets the same amazing results, but without needing all the complex machinery. It's just a fantastic example of elegance and power in algorithm design.
So, what's the big takeaway here? Quality diversity algorithms are this incredibly powerful way to explore the full range of possibilities for a problem, and they prove that a simple, intuitive idea can totally match the performance of much more complex methods, as long as you define your bins in a way that actually makes sense for the problem you're trying to solve.
And this leaves us with a final thought to chew on. This shift from finding a single solution to curating a whole collection of them could fundamentally change how we tackle problems in science, in engineering, even in art. What kind of new discoveries are just sitting there waiting for us in these unexplored solution spaces?